Hey everybody, it's Mr. Carr again. Today we're going to be looking at 7.3 day 2. We're going to look at some other types of regressions besides linear by focusing on quadratic and exponential regressions. So what does that mean? Now, when we look at these two scatter plots here, a straight line is not going to be the best fit necessarily. So for example, here we look at the line here seems to be it seems to be dipping down, and then my trend is going back up. So whatever the scenario the scenario that's being measured here, it has this trend of going down and coming up. That's not a straight line. That's more of a parabola shape. Okay. So when we see that, draw it in blue here. Like this, we get a parabola. Then we can do this as a quadratic regression. Same idea here. My trend line, I could sort of do a straight line here, but that doesn't really fit very well with what it seems like going on. Seems to be kind of going this way and then curving up, kind of like an exponential curve. Okay, so that's our two things we're going to focus on today. We're going to be exploring a quadratic and exponential regressions that represent our data that's not necessarily linear. And that's the key here. It's not linear in this case. So we can create a quadratic regression, exponential regression the same way we did our linear regressions. We just need to look at the scatter plot first to determine which one would be the best fit. Okay, so just like you do in you do your L1 and L2 and everything in your stat edit and everything like that. But one thing you want to do is before you do any regressions, you're going to want to go to zoom stat. Okay, and decide whether you think the data is linear, quadratic, or exponential. And then you can go to your stat and then calc menu from there and then select your option. So option 5 is our quad regression. If you think the data is quadratic, and then exp reg if your data is exponential. I'll be doing this in Desmos, and my mind's a little bit easier personally. So when we do this here, okay. So when you do this, make sure you understand your linear regression, ax plus b, quadratic is ax squared plus bx plus c, y equals ab to the x power. So you're getting those parameters like A, B, and or C when you do these types of regressions here. So the other thing you can do is if you're unsure, this one's not like the first thing to do, it's one of the last things you should do, is do all the regressions and then start comparing R or R square values for quad regression. Okay. It doesn't quite do a quadratic or sorry, a correlation coefficient in a quadratic regression, but everything else you can kind of compare. The closer you are to 1 or -1, the best fitter that is. So if something is only like a 0.8 and something else is a 0.9, probably the 0.9 is going to be the better fit. Okay. Now, so our first model here, we got pumpkin tossing contest. It's held each year in Morton, Illinois, where people compete to see whose catapult will send pumpkins the farthest. One catapult launches pumpkins from 25 feet above the ground at a speed of 125 feet per second. Table shows the horizontal distances in feet the pumpkins travel when launched at different angles. So we're comparing angles to distance traveled. So use a graphing calculator to create the scatter plot. So I've already done that here in my Desmos. Now I'm going to go ahead and hit this magnifying glass here. So you can see how there is a trend of going up and then coming down. This leads me to believe that it's a quadratic regression. So that's going to be my choice in this case. Okay, I'm going to say quadratic. The trend goes up and then down. Okay, so that means I'm going to now do use my graphing calculator to do that. So again, if you use the TI-84, look back at where you see those steps on there. But for us, we're just going to do this. We're going to click this button here. The automatic is a linear regression. You can also see how that does not fit very well. Put that a little thicker there. So I'm going to actually click the little drop-down menu and choose quadratic regression. Now you can see it's a pretty good fit there. In fact, R squared is a 0.99999993. This means that really high percentage of the values are a close fit to the line. That's what the R squared is telling us. It's a little bit different than the correlation coefficient, but for our purposes, as again, if R squared is closer to 1, the better. So now I can go ahead and use my model here. So it's written, yeah, so it's right here, this point negative 0.26 x squared plus 22.59 x plus 23.03. So let me go ahead and write that down here. So y is equal to a negative 0.26x squared plus 22.59x plus 23.03. Now remember, what is x in this scenario? When I go back here, x is the angle, y is the distance traveled. So that means when I look at the follow-up question, use the equation to predict the distance that will travel if you use a 25-degree angle. So y is going to equal to a negative 0.26 times 25 squared plus 22.59 times 25 plus 23.03. Just plug that in the calculator there, and y is going to come out to about 425.8 feet. Okay. Next one, again, I've got that on information. We got deer population starting in each month starting in January. So January is equal to 1 in the scenario. Okay, so let me go ahead and switch over to this one. I'll do my zoom fit here. Let's turn off this quadratic. There we go. So when you look at that, it seems to be a curve going upward. I don't think it's like a linear one is going to be a best fit here. So I'm going to go ahead and click this, click instead of my linear regression. Just for comparison, you can see that r squared 0.933, r is 0.9661. That's a strong correlation. But if I go do exponential regression, it's actually a little bit higher. And the other thing I want to do is you're going to click the log mode. Okay, just always plan on doing log mode. It's just something that is what's it called? Something that's always going to be a part of using Desmos. Okay, so you always choose the log mode there. So now I've got my parameters. Y equals 8.46 times 1.42 to the x power. Okay, so let me write that. Oh, sorry, I'm going to choose exponential. And again, the curve seems to have this, or it seems to be an upward curve versus a straight line. So that's why I'm choosing that. Okay. So when I do this, my y is equal to an 8.46 times 1.42 to the x power. Use your equation to the deer population after 13 months. So that's going to be x is equal to 13. So we're going to do y is equal to 8.46 times 1.42 raised to the 13th power. And that comes out to about 807. Yeah, I'll write that a little better. 807 deer. Okay. Hunting season begins when the deer population reaches 200. Between what 2 months should hunting season begin? So on this one, again, with Desmos, it's really nice. Now, I've got everything saved here for the equation. After 200, I can kind of just scroll a little bit and I look on the curve right here. So I can see that it occurs right here at, let's see here, basically after 9 months, but before 10 months. So it's doing that. I can also do this where I can do y equals 200. I can find the exact point that they cross like that. So it's after 9 months. So it's like right just a little bit after. So I can do that from the graph. It's going to happen between 9 and 10 months. Okay, so again, that's the nice thing about Desmos. You have that graph there. You can just kind of refer back to that. It's pretty easy to go back and forth between the two and then see where you're at with those. You can technically solve this also with logarithms, but your logarithm would have gotten the same answer that I just got from my finding my intersection point. Okay, so that's just something to call back to some of the things we've done before too. All right, so that is it for today. Again, we're adding on to our linear regressions by doing both quadratic and exponential regressions on here. Just make sure that you're always doing like the zoom stat or that zoom fit window and double checking how does the trend look to you? Is it quadratic like this, or is it going down and up? Is it an exponential curve that does that? Or is it just a straight line? And then you choose your regression based on those things. All right, that's it for today. Take care, everyone.